Right, so let's have a look at the Heartbleed vulnerability, and we'll look at a basic history of it. So in the first section we'll have a look at the basic outline, some of the background information around Heartbleed, and then we'll go and look at what it is based on, which is SSL, and then the protocol which actually caused the problem, which is around the heartbeat with inside SSL and TLS, and then on to look at a real life demo of Heartbleed and the basic timeline of what happened before, during and after the vulnerability was found. And see, these are some of the comments that have been made by Bruce Nair. On a scale to 1 to 10, then this is an 11. So this shows the type of impact that it could have had with inside the industry, and especially when we look at the market share of something like Apache servers, which are vulnerable. So any Linux-based servers could be vulnerable to it, because they could be using this Openssl library. So Microsoft's share has really dropped with IIS over the years, and the LAMP stack, Linux, Apache, MySQL and PHP has really taken off greatly and is used by many of the web infrastructures around. And his viewpoint is that Linux is used in many embedded systems, and it could be very difficult to update those embedded systems without actually getting rid of them and buying something else. So let's do a quick review of what cryptography is all about, because that's the core of what we're going to be looking at as part of Openssl. The three main methods that we have in cryptography are symmetric encryption, asymmetric and one-way hash. Normally you'll actually find that all three of these things go on at the same time, and they have different types of functions. The most widely used cryptography is actually symmetric encryption, or what's called private key. One key is used to encrypt and the same key is used to decrypt. So this is really the workhorse of the industry, and it is typically used in many applications, sufficient in its encryption and decryption process. AES is a good example of this type of encryption. Then we have public key encryption. We generate a key pair. One key is used to encrypt, and another key that's generated is then used to decrypt. RSA is a good example of public key encryption. And then what we have is a one-way function or a hash function, where it's very difficult to mathematically go back to the original, so that we have just something that goes in one direction and creates a fixed format hash signature. Unfortunately, this can be easily hacked by creating what's called rainbow tables, where well-known hash signatures are known for certain types of plain text. Normally what we have in cryptography, and especially in something like SSL, is that we actually have all three of these going on at the same time. A private key is used to be able to secure the connection using a session key. So when we connect through SSL or TLS, we have a session key which is unique for each session that we create with a web server or with a remote server. And this key times out, or will be changed for the next connection. So it's not really possible to crack that key, because we don't really have time to be able to crack it. The time we crack it, then there is a new session created and so on. So the way that the key is created in something like SSL is that we have a method such as Diffie-Hellman, which allows a key to be created by Bob and Alice communicating with each other, and they will end up with the same shared key. Public key encryption is typically used to be able to identify entities such as the remote website. So when Alice sends over her certificate, it has her public key in there, and Alice signs things with her private key. So we have a private key here which she keeps secret. Unfortunately, so anyone who gets Alice's private key can actually sign things on her behalf, so it looks like her. What happened with Heartbleed is that some of these private keys could have been released, which compromised the system, so that Bob could have viewed Alice's private key and then can actually pretend to be Alice to other systems. So as we've seen it from Bruce's comments, then there was a whole lot of server revocation going on. Over 500,000 certificates were revoked because no one quite knew if these private keys had actually been stolen. And then in the end, if we want to authenticate the messages that we send, we typically use a one-way hash to be able to check that the message is correct at the other end. And so now let's have a look at the Openssl libraries. So the history of them was that they were originally developed by Eric Young and Tim Hudson, and they created this SLEA, and the EAY is actually Eric A. Young. So when they finished their research, they went to work for a company, and it was handed over to the Openssl Software Foundation, or OSF, and their first version was 0.91 in December 1998. So the Openssl Software Foundation is run by Steve Marquez and Stephen Henson. One is based in the US and the other in the UK, with a number of volunteer developers and with a fairly minimal budget of less than $1 million a year. It's funded by various agencies, or it was funded by various agencies, such as the Department of Homeland Security and the Department of Defense. So the code in it increased over the years until we got to 1.1, released in March 2010. But what happened for 1.01a was that this heartbeat support was added into TLS and SSL, and it was this thing that caused the vulnerability. It has been there for quite a while, and it was discovered it was announced around the start of April 2014, and it went through various iterations. It's now 500,000 lines of code here. Up to A to F were vulnerable, and then it was patched, and G onwards does not have the Heartbleed vulnerability. So for OSF, it's led by a full-time developer, Stephen Henson, a UK-based mathematician who wrote about 60% of the overall code. And then just at the end of December 2011, Robin Siegelman, as we'll see, who wrote the RFC around Heartbeat, actually implemented the code, and then that was okayed by Stephen Henson and it was released as an update. Stephen Marquez has since said that they have very little money going forward with Openssl to be able to perform code reviews and audits and so on, and the funding has dropped drastically after the Heartbleed vulnerability. And he has asked, where are all the Fortune 1000 companies now who actually use it for free? And the funding has dropped drastically. When you look at the code, you actually see some startling comments, and the code looks quite messy. The variable names aren't really very descriptive, and it's quite terse in places. Obviously C is like that anyway, but some of the comments are quite worrying when you actually see from it, and we'll see language such as this, which isn't really very professional language with inside the code, and things like eek experimental code starts here and eek experimental code ends. So you can see that possibly some of the problem, or the major problem, has been caused by the lack of the review and sloppy code. But OpenSSL itself is a fantastic library and is extremely useful in checking cryptography and making sure that that things are actually have been checked. The algorithms themselves are typically very strong in terms of what they actually produce, so it's still a very useful program. So if we run OpenSSL inside our console, we can see the version. In this case, we have an unpatched system 1F. We can also use it for hash digest. This is MD5 of a file, produces this. This produces our RSA key pair, and then we can extract the public key from there, and then we can even print it out. So it's a very useful program, and it's free to use. It also does salting of passwords. So in this case, we take this and we take some salt. The salt is here. We add them together and we get this hash signature, which makes it very difficult for an intruder to actually break. Okay, so it shouldn't really be dismissed because it's a very powerful library. And so now let's have a look at what caused the problem. And the thing that caused it was this RFC here. What we have in a stack, in a network protocol stack, is often there's a place that allows us to be able to check if the other side has disconnected. This is done with inside TCP quite well with timeouts, and it's also done at a higher level layer, typically in the application layer. This specification here for this RFC was intended so that one side could tell if the other side was still alive as part of the SSL connection. So it's not really needed too much, but it's a very poor RFC, and it was written by the chap that we saw before, who actually implemented the code. And this is the basic format. So the structure here, this is a 1 for a request, or a 2 for a reply. And then we have the length of the payload, and we have the payload here. So straight away there's a little bit of redundancy that we can actually see, and that why do we need the payload length when the payload length is actually in here anyway? So it's not too difficult for a computer, the receiver, to be able to look at the payload and calculate the length. So this is the thing that really caused the problem. This itself is arbitrary content. It doesn't really matter what it is, it's just a certain size of content. Again, you've got to wonder why you would even need a payload in there to be able to just define if a machine is alive or not. Okay, so if you keep those thoughts there, we send through the payload length, and we send through an arbitrary payload with some data into it. And what we want to do is to get the server to send that arbitrary payload back, and we know that the machine is still alive. A disaster of a protocol, really. But it was approved and it was implemented, and it really didn't work very well. Okay, so let's have a look at the Heartbleed vulnerability itself and see what it actually did. Okay, so here is the code that caused the problem, and let's remember what how the payload was actually, or how the protocol was implemented. So what happens here is that we determine the size of the payload here from the packet that's sent, and this is the payload. So basically what's happening is that really we should never trust the user input at all, and we should always check. But what can be done is that our system can say here's the payload, 64K, but the payload itself can only be just a few bytes, or can be 0 really. Then what happens in this code is that it allocates an area in memory. Okay, so in many systems the memory isn't cleared, so there is memory running there. So what it does is say, right, let's take this memory and we'll allocate it 64K, say. And then what the program does is it loads that the payload into the memory. So in this case there's 8 bytes. Now it gets loaded into memory, which still has all the program variables and other things that have been left in there because the program hasn't cleared it. And now what we have is we have our old memory still there, and only a bit of it is overwritten by the payload. This is then sent back to the other side. So the intruder gets to see 64K of random memory each time that they access, and we'll see variable names and keys and things like that over the time period. So this is where, if the system was a patch, then users should not have changed their username and password, because by logging on they go and their username is in there and their password could be in the running memory and it's unpatched, so an intruder could actually glean this information off. Okay, so that's the operation of it, and that's really what caused the problem. To overcome this, basically all that needed to happen was there was a check to see the size of the received payload was actually the same as the payload size. So here is a copy from a real vulnerability probe. So here is our, within SSL, 18 defines heartbeat. There is the 18 there. Okay, so we're using 443. So this is from the client to the server. So we're using 443. So we should be able to see anything that is recognizable in terms of plain text and so on, because this is encrypted. We should be able to read anything, but as we'll see, that's not quite the case. This defines TLS 1.1, or we can have SSL in there, depends what the server is working on. And this is the length there of the packet there. Then this is 1 for a request, and we get 2 for a reply. And here is the problem here. It's now saying that my payload is 16K in this case, because 0 hex 4000 is 16K. So we can see here that the packet is actually not correct. There's virtually no data in there, but it's spoofing it by saying it's actually 16K. The response that comes back, again we're using 443, but we actually see that what comes back is the running memory. So what it does is it sends back a packet which actually contains the memory. So we shouldn't be able to see anything here because this is 443. It should be encrypted, but we can see it hasn't encrypted it because it's sent back just a dump from the memory. Okay, so let's have a look at a live demo. Okay, so what we'll do is we'll run up a Ubuntu server. That's not the right one. Okay, so this is our Ubuntu server here. And then I'm just going to open up a terminal. Okay, so this is all running in a private address space, so there's no public networks here. So let's actually have a look at our OpenSSL. Okay, so what you can see here is 1.01e. So you can see that is a vulnerable server. We'll just have a look to see what our IP address is. 172.16.168. 121. So just to show that it actually works, so let's do 19172. So just to prove this is our address here. Do we find it? Okay, so we are on 172.16.121.1, and we're contacting this address here. Okay, so this is running a web server, so we'll just contact the web server and everything is fine. Okay, so that's good. So what we're going to do is we're going to run our Python script, and before we do that, let's have a look at what the Python script actually looks like. Okay, so there's the vulnerability there. So this is what gets sent. So there we go. There's the 40. So if we remember where we were, there we go. Okay, 180301. That's for SSL. There's our 02 there. 031400. So this is what gets crafted to be able to get sent to the other side. Okay, so we take this and then we decide if it's a SSL or a TLS, and then from there we can craft the Heartbleed hex values to be able to send it to the other side. So it's as easy as that. Okay, so let's now quit from here. And let's run our Python script. So it doesn't take too much expertise to be able to do this. Okay, so that's going to then run against our server, which is at 16.121.150. So it's connecting into the server. Just taking a little minute to do that. Let's check. Do we have the right? Oh, we don't have the right IP address. Let's try that again. So here we go. Then that's the right one there, and there we go. Okay. So what we'll do is we'll just show that one page at a time. Makes it easier to view it. Okay. So what we actually see is that when it's sending, so it's TLS 1.1 there, and there is our values coming back. That's the 16K. That's the length of the packet that's actually received back, 16K. And there it is there. And what we see coming back, not too much information there, so let's try it again. Maybe we'll see something. Oh, and there we go. So you can actually see that there in memory is some text information. If we're very lucky, we might see some session information from a cookie. So what we'll do is we'll try and refresh that just to see if we can get something in memory, such as a cookie. And there you go, a little bit more information there, so that we can just keep having a look. And it's given us different memory each time. There we go, there's some more memory. Let's see, it's not too difficult. An intruder is often after some session information. And we can see each time we're getting some more information. And we can actually pick off things like encryption keys and so on. So you can see it isn't too difficult to be able to, for an intruder to be able to exploit the vulnerability just by running a little Python script. Okay, so if you're interested, we have actually set up a web page which actually has a Wireshark trace of Heartbleed for you to be able to examine the network trace. If you look at network forensics, and here we are here, and that should hopefully pull up our Wireshark trace. Okay. Okay, so you can see how easy it is to craft, and then how easy it is to get this information back again about the 16K data packet that comes back, and we can see it's non-encrypted. And so for our final section, let's have a look at the timeline of what happened before, during and after the Heartbleed vulnerability was announced. So the rough timeline was something like this. So Robin implemented the code around Heartbeat. It was committed New Year's Eve 2011. Roughly 2 years and a bit years later, it was actually discovered. So it had been around for 2 years and lay undiscovered. So on the 1st of April, Google actually informed the Openssl Foundation that they had found the vulnerability, and it was Neil Mehta that found it. And then at around the same time, this Finnish company actually found it too and dubbed it Heartbleed. Then the announcement happened around the 7th of April. So quite a terse email said, "We are doomed." And then it was found on the 8th of April that half of the websites that were sampled had no SSL, and then about 15% were actually exposed to the vulnerability. And Neil actually received a bounty for finding the bug, and then donated it straight away to a group of open source encryption tools. The detail is a little bit patchy, but let's look roughly at what happened. So it was discovered sometime around or before the 21st of March, at which time Google patched their own systems. And then Cloudflare patched their systems too, where they found out that a friend said it was messy. Then Google informed the Openssl team on the 1st of April, and who distributed the information to the rest of the team. And a day after that, the Codemacon company discovered the same bug and informed the National Cyber Security Centre in Finland of the bug. After that, the Acme.com patchers servers were patched, and then there started to be rumours around the 4th of April, and then the Heartbleed.com site was actually registered on the 5th of April, and they asked that the National Cyber Security Centre in Finland search for a CVE number without actually giving any detail as to what it was. So this is the registration here for Heartbleed.com. We can see it was the 5th of April. This is how the page eventually looked, but we can see here it's running with inside Amazon services. They had registered quite a few Amazon instances, IP addresses, probably knowing that it was going to be extremely popular. Okay, so there's the creation date there. So if you actually look up the Wayback Engine, you actually see that in 2005 it was a very different website. So Heartbleed.com looked like this at one time, and it was an emo site with lyrics related to typical emo lyrics. Then, if you look at way back on the 8 p.m. on the 7th of April, the site looked like this. Just obviously prepared to go live and then define the information that was found by this company here. Now, this is what it looks like. So after this, Mark Cox, who was also part of Red Hat and Openssl, added a private bug fix to their code. Then Facebook patched their systems, again informed through a friend. And then the National Cyber Security Centre in Finland reported the bug to the Openssl team via an encrypted email. Openssl then fixed the bug and posted a bug fix for it, after which Cloudflare published details, Neil tweeted, and then Cody McCon tweeted their details too. And this is the profile of the activity around tweet. We can see tweeting, we can see a low, virtually zero, around the 7th of April. It starts to kind of take off, so there is some information happening around the 8th of April, typically around technical, but then the news around the world took hold of the story, and we can see a peak happened around the 11th of April as it really broke. It then has tailed off over the days after it until it's dropped to, again, very low level on the 14th of April here. And this is the sentiment. You can see that there is a lot of bad sentiment around the Heartbleed, some positive stuff, but mainly negative. One other thing that can be observed is actually in the stock prices of the companies involved. This is Yahoo, and these are the days before Heartbleed actually was announced. I can see Yahoo takes a massive hit in the days before it, and we have lost 10% of the stock before it was even announced. The same with other companies. Google did very badly here, AOL, and so on. So most of the major companies that might have been affected actually were hit hard. So this could be insider trading here, or insider dealing, where the technical updates have been leaked to those involved in the shares, buying and selling shares. I can see they bailed out in order to bail back in and make a good profit. So you can see the price went up, but then it really hit the global news, and again the stock was bailed out and dropped again. So this looks a very strange pattern indeed, where it was only here it was announced, but many of the companies knew about it with inside, or quite a few companies knew about it with inside this time period. It recovered because it was a kind of technical thing here, but then when it really hit, then the stock price fell actually again. And the one that was hit hardest was actually Yahoo. And the reason that Yahoo was hit was that the screenshot that came from the vulnerability being published was actually a Yahoo address from their email system. So it was obvious that they were going to be hit quite hard because it had actually released an email, in a Yahoo email in here. And we can actually see the email there, Agnes Abu Boteng. And it was rather unfortunate for Agnes because Agnes's email address was actually contained in the vulnerability report. If you search, then you actually find that she comes from Ghana, and there is even information on the internet related to her cell phone number, and so on, and there is other information around her. to show how the news can be picked up. In this case, we published the Heartbleed bug and the insider trading announcement. It appeared in The Conversation, which is an academic publishing agency inside high quality academic publishing agency in the UK, which picks up news items from universities. That was then taken on by The Independent, and then if you actually look from there, those two stories as a source then went on to become 46,300 news items. So these actually have the complete text from. So this isn't just this is a complete copy of the title. It is then what these two stories was then picked up by over 46,000 news items from them. So where are we going? Well, on the 24th of April, the whole industry agrees that this is a major problem, that we need to create much stronger infrastructure for the internet. So some major players have provided the funding for this core infrastructure initiative, which will allow these new libraries to be created. If we look at it, the Apache Foundation has less than 1 million, Linux Foundation about 6 million, and then the Mozilla only has 311 million. So it's important that organizations fund the development in order to produce strong code. And it looks like that will be funded by 3.9 million for the next 3 years. And the top of their list is Openssl. Okay, so that's provided a short history of Heartbleed. Where are we now? Well, it's kind of went away, but it was an interesting bug vulnerability as it was. And what we really have is other vulnerabilities that are actually just as severe, such as these three here: the Java exploit, the Flash exploit, and the PDF. The Flash exploit are all severe exploits that on an unpatched system can cause many problems. Okay, so that's been a quick introduction to Heartbleed.